Hello and welcome. I'm Dr. Zachariah Renfro, and today we're going to talk about inductive reasoning and probability. So, starting off, let's kind of talk about what the overview of this lesson is. This lesson is mostly about how different probabilities can play into our arguments and how we can use those probabilities to make inductively sound arguments or cogent arguments. So let's start with some inductive quantifiers. Those are words such as a few, most, some. Those are things that designate that you're not talking about the entire group of a thing, you're just talking about a select number of the thing, right? That plays into probability and inductive reasoning because a lot of times you'll see probabilities related to small groups. Some dogs are brown. Every dog I've seen so far has been brown. Therefore, the next dog I see is probably brown, right? So we've got this idea of relating truth to groups of things, but that those things are not quite the entirety of the thing. It's some set of a larger set. With that being said, let's move on to some of the meat of our lesson, some of the definitions. So first we've got inductive force. That's an argument that's not valid, but it still could be true. So for example, I live in Kentucky, therefore I must eat KFC. Now, the fact that I live in Kentucky has very little to do with my dietary habits, right? We can't draw a direct line from living in Kentucky to eating KFC. However, it's a very reasonable assumption that if I do live in Kentucky, that I probably would eat KFC. Next, we've got inductive truth. For something to be inductively true, you have to know about the subject, right? So if I tell you every bear I've ever seen is white, therefore all bears must be white, you obviously know that that's not true, but in order for you to know it's not true, you have to know a little bit of something about bears, right? That statement wouldn't make any sense if you didn't know anything about bears. Next, we've got inductive soundness or cogency, right? That's an argument that's not valid, but is forceful and it can still be true. An argument is cogent if it is sound and we believe it to be true. However, there can be arguments that are cogent, but that we still might reject the premise as not being true. So for example, every president so far has been over 40 years old. The next president will likely be over 40 years old, right? So we've got good evidence. All the presidents before were older than 40. We have reason to believe that the next one's going to be older than 40, but we could still reject it because maybe the next president is only 39, right? Next, we've got probabilities and degrees of rational expectation. Rational expectation just means believability, right? So when presented with an argument, that is whether or not you can believe that the argument is true. Probability plays into this because with our book and with many other books that focus on introductory logic, these probabilities have specific numbers that relate to their likelihood of being true. So for example, probable is 50 to 99% being true. Likely/not likely is 1 to 49%, and certainly is 0 or 100%. And we see this right here, starting at 0%, it's not valid, not forceful. We get up to 50%, it's still not valid, but it's starting to get forceful, right? So when the closer you get to 100%, the more likely it is to be a forceful argument. And a forceful argument being one that's not valid, but still could be true, like the KFC example. So with degrees of rational expectation, the way we want to look at it is if something is probable, we've got a good reason to believe it's true because conventional implicature, right, the way that people use the word probably, doesn't just mean 51%. It's more closer to 75, 85, 95, right? Because the way people use the common word probably in common conversation would mean that if something's probably true, it's more likely than not true. Next, we've got inductive inferences. That's when you take a small sample size and you extrapolate from that to a larger set. Every goldfish I've ever owned has died when I fed it dog food. Therefore, the next goldfish I get will die if I feed it dog food. You can see how I'm drawing from that small set, every goldfish I've owned, and I'm extrapolating it to the larger set. So the next thing is the fact that premises can be probabilistic or they can be absolute. So for example, you can have a premise that says, the next time you flip a coin, there's a 50% chance it will be heads. You could have a premise that says, the next time you flip a coin, it will be head. One is absolute, one is probabilistic. From that, we can also understand that some premises are dependent, probabilistically dependent on each other, and some are independent. So an independent premise is something like the fact that if you roll a dice 2 times, the numbers that you get have no relation to each other. However, if you draw a card from a deck of cards and you don't put it back and then you draw another card, your second card, what you get, has some amount of bearing, even if it's a small amount, on the first card that you drew, right? So they're dependent on each other. Then finally, I need to talk a little bit about the difference between proportion and frequency. Proportion is a percentage of a thing or of a set. 51% of all women have hair, whereas frequency is a percentage over time, right? So 10% of Decembers have snow. So that's the difference between frequency and proportion. All right, so let me show you 4 styles of inference. I'll go through them 2 at a time to help you understand some of the ways that people will use extrapolation to make points about things. So first we have to define our terms. So starting with probably, right? If we're going to use the word probably, we have to know what that means. So the probability of phi is greater than or equal to 0.5. And I'm going to truncate it to the probability of 5. So what does that mean? Like I mentioned about common implicature, probability of being greater than or equal to 0.5 means that it's more likely, right? It is like 70%, 80%, 90% instead of just 0.5. Next, we've got epsilon, which is this funny looking E, and that'll stand for a set. Then we've got epsilon O, which will stand for the observed set. Capital F will mean fish. Capital G will mean goldfish, and then the minus sign will be the negation. With the capital F, we'll have one later where we will have a lowercase f. The lowercase indicates that it is a specific of the set, right? So this is the set of all fish, and a lowercase f would be one specific fish, like you caught a fish, right? So starting with style 1, this is one you'll see very commonly in things such as medicine commercials or articles about different scientific studies. In the observed set, if it was a fish, then it was a goldfish, right? So we're saying that all the fish I observed were goldfish. So probability of phi, probably all fish are goldfish, right? So probably, and this is the universal quantifier. If there's a thing that's an X, with X being fish, then if it's a fish, it's a goldfish, right? So this is saying I saw a bunch of goldfish when I was looking at a set, and then this says that all fish must be goldfish because of what I saw looking at the set, right? We obviously know that not all fish are goldfish, right? But you might see something like this. Of the people observed in the study, none of the people got sick. So therefore, anyone who takes our medicine isn't going to get sick, right? A person could still get sick, or maybe they didn't observe enough people to see someone get sick, but that's how this type of generalization works. The second style of generalization works like this. In our observed set, if it was a fish, then it was a goldfish. Probably this fish that wasn't in our set is a goldfish, right? So Let's break this down a little bit more specifically. In the observed set, epsilon O, if something is a fish, then it's a goldfish. So probability phi greater than or equal to 0.5. We've got the negation of the observed set, right? So the thing that wasn't in the observed set, and it was this fish, right? We've got the lowercase f. It was this fish, therefore it must be a goldfish, right? So we're taking from our observation and we're applying it to a specific thing we didn't observe. Taking from our observation, applying it to a specific thing. All the car crashes I observed were caused by drunk driving. So if you're a car crash, then you're drunk driving. So probably this car crash on the road is because of drunk driving, right? Now again, we know that this can be false, but it is a common type of argument you will see. So on to our last two examples, style 3, y% of the observed fish, if they were a fish, they were a goldfish. So y% of our observed set, if it was a fish, is a goldfish. Therefore, it's probably the case that y% of all fish are goldfish. So let's break this down with a little bit more detail. We're saying y%, so let's say 10%. 10% of all the fish that I've observed were goldfish. So probably 10% of all fish that are alive are goldfish, right? And being more specific, we've got our percentage, y%. We've got our set, a set of observed things. If it was a fish, then it was a goldfish. So 10% of our observed fish were goldfish. Our probability, we've got our universal quantifier. For all fish are goldfish. So what we're saying is X% or Y% of all fish are goldfish. Moving on to our next one. This is one that's a lot less common. You don't see it as much as you will see this one. This one you'll see, for example, a heart medication. 10% of all the people we observed who took riboflan had improved cardiovascular activity. Probably 10% of all people who take riboflan will have improved cardiovascular activity, right? Now onto this fourth one. This is one you don't see a lot. Y% of the observed set, if you are a fish, then you're a goldfish. So this one changes the probability. The probability is now greater than or equal to Y% that this fish that wasn't part of my observed set is a goldfish, right? So we'll go through this piece by piece. Y%, that's our percentage of the fish that were goldfish. This percentage of the fish that were goldfish, right? We have our observed set and the fish that were goldfish. So this is actually speaking about this. And we see that up here, right? This percent of the fish are goldfish. Now, what happens is, though, for this argument, it's actually moving down here to become part of our probability. So our probability is now greater than or equal to. So let's say that this is 10%. And now, see what happens. 10%. 10% of the fish we observed were goldfish. So there's a 10% chance that this fish that we didn't observe is a goldfish, right? So let's go through that again. We've instantiated this to 10%. 10% of our observed fish were goldfish. So there's a 10% chance, that's what this is saying, a 10% chance that this fish, which we didn't observe this fish. We don't know where this fish came from, right? We don't know where this fish came from because we've got the negation of epsilon. We don't know where this fish came from. It's a goldfish, right? So like I said, this argument structure is a little bit less common, but you will see it sometimes. And this argument, you know, if it was in a medicine commercial, it'd be something like 10% of the people we observed who took Suboxetran got better. So there's a 10% chance that this person we didn't observe, if they take Suboxetran, will get better, right? So that's how that works. Like I said, it's not as common as styles 1 through 3, but you will see it sometimes. All right, let's try and translate a couple of these live. I've not tried to translate these before. I don't know how they're going to turn out. I usually have my lovely assistant read them off, but today I have to read them off solo. So let's see how this goes. Most children love Harry Potter books, therefore your child will love Harry Potter books. So we've got our observed set, epsilon O, and if it's a child, then it will love Harry Potter. All right, epsilon O, child, Harry Potter. Therefore, your child will love Harry Potter. So, therefore, your child, who is not part of the observed set, and a little c, will love Harry Potter, right? Our observed set, children who love Harry Potter. We have your child, who wasn't part of the observed set, and they'll love Harry Potter. Let's do another one. In countries colonized by Spain, there are many people of Spanish descent. A minority of people in Laos are of Spanish descent. Therefore, Laos was not colonized by Spain. So let's work this out. We've got our observed set, countries colonized by Spain. And if you were colonized by Spain, then you'll have a lot of people if you were colonized, then you'll have a lot of people of Spanish descent, right? So that's our first one. A minority of people in Laos are of Spanish descent, so we're going to put not S and Laos. Therefore, Laos was not colonized by Spain. Therefore, Laos was not colonized by Spain. Laos and not colonized. So we see this here in our observed set. If you're colonized by Spain, then you have a lot of Spanish people. Laos does not have a lot of Spanish people. Therefore, Laos was not colonized. All right, let's do another. If Hansen is leaving early tomorrow, then probably he isn't in the bar. Hansen isn't in the bar, so he's leaving early tomorrow. So let's put our probably. Probably, if he's leaving early tomorrow, then he isn't in the bar. He isn't in the bar, so he's leaving early tomorrow. All right, let's do one final one to wrap us up. Most vegetarians eat eggs. A great many people in Berkeley are vegetarians. Roger is from Berkeley, therefore Roger eats eggs. So our observed set is vegetarians. So let's erase this real quick because we're going to need some room. So we've got X% of vegetarians. We've got X% of our observed set. If you're a vegetarian, then you eat eggs. Many people in Berkeley are vegetarians, So Y% of the people in Berkeley are vegetarians. Roger is from Berkeley. So we got a little R for Roger because we're talking about a specific guy. Roger's from Berkeley. Therefore, Roger eats eggs. So we've got, from our observed set, some percentage of them are vegetarians who eat eggs. From another observed set, Y% of them are people from Berkeley who are vegetarians. Roger is from Berkeley, and Roger eats eggs. When it comes to argument translation for inductive arguments that use probability and use quantifiers such as most, many, some, we see that it can make our translations of sentences a little bit wonky. And these translations here are a little bit simplified. They're not exactly the same thing you'd see if you was taking an advanced logic course. But the goal is to kind of help you understand how to think about these things, right? If someone says to you, 90% of people who take riboflavin lose weight, you have to understand what they're saying. They're saying they observed some people who took riboflavin and lost weight. And then they're going from that to the next step, which is if you specifically take riboflavin, you'll lose weight, right? We have to understand how these tricks of implicature work. That way we can understand how to analyze inductive arguments, because analyzing inductive arguments can be a little bit tricky because inductive arguments themselves require you to understand facts about whatever it is you're talking about. Now, sometimes you can break apart an inductive argument just on the basis of it, and that's why we write down the forms of the inductive arguments. That way we can see, these things don't follow from each other, but it is always helpful to understand how these things go together. That way you can effectively use them. So with all that being said, I hope this was helpful to you. If you're a student in my class, I can't wait to hear your thoughts. If you're not, please comment in the forums below. Let me know what you think. I know this stuff can be complicated, and I appreciate you sticking it out to the end, because learning this stuff will help you in understanding what it is people are trying to say. So thank you very much for your time. You have a wonderful day.